Thank you, everybody. Thank you for the introduction, and thank you very much for the invitation. It's really lovely to be here and celebrate CEREGE's birthday with you all. So the title of my talk is Climate and Ice, from Rising Seas to the Mountain Water Crisis. I tried actually to translate a few some of the phrases in French, and I'm not using artificial intelligence, so there's probably tons of errors, but it's at least authentic. So we are working on almost anything that's kind of changing ice and has an impact on the sea level or on other areas of societal well-being by now. And before we start, I just want to have one slide. So what are we actually celebrating here? So CEREGE really has become one of the big leaders European-wide and globally in environmental climate science and education. I really like that sentence on the webpage, the pôle d'excellence de par ses compétences humaines et ses capacités instrumentales. So the fact that the compétences humaines come before the capacity instrumental is, I think, really essential and really clever, and it's really important. This does not mean that instruments are not important, but obviously we are doing all of that for making the life better for communities and for people and for our planet. So there's also clearly a growing strength in societal relevance and climate justice related projects in CEREGE, which is also really the future, I think. And the one point that I want to make, which is really getting more and more important, also CEREGE has been a refuge and a safe and fertile place for academic excellence and freedom. And that has been really a refuge for many scientists and AMU also is kind of Aix-Marseille University has several of these refugee programs, which are really impressive, and that is, I want to celebrate that, and thank you for that. This is really super important, will be more and more important in the next years. So, Allez, CEREGE and AMU. So very quickly, a few highlights. So when I came to Lamont in 2001, it was 10 years after Bruno Hamelin and Edouard Barr basically ushered in a completely new era of geoscience and sea level science in particular, by being able to use uranium thorium to date corals and to use several of these archives to calibrate the radiocarbon curve and use the coral reefs for direct observation of past sea level. So that was kind of really in a good spirit and classic spirit of Lamont, it's kind of development of new methods, also new instruments, but not just for the sake of it, but with a clear goal in mind and with a clear target. And I think that has Lamont has carried on to do that. And I think that's also kind of what CEREGE made so special, that you have the space and opportunity to develop new things, but not just for the sake of it, you really have a goal. So that is kind of an institutional connection, I think. And then there's tons of personal connections. When I started in Lamont, I started working with Bob Finkel right away, which was a wonderful professional and now personal relationship. And Bob was also the postdoc advisor of Lucilla Benedetti. And then Lucilla Benedetti was a PhD advisor of Irene Schimmelpfennig, who came then, Irene came to Lamont and is now back since a long time and carried on the cosmogenics, or established the cosmogenics here. Vincent Rinterknecht was my first postdoc in Lamont, is now here too. And Vincent Chomely was with Irene supervising Joanna Charton, who is now a postdoc in Lamont, and I will show her recent results in a second. And then, of course, I always have been interested in analytical excellence, or pushing analytical methods, and Didier Bourles, great Didier Bourles, great and very missed Didier, and now Régis Projet and the Astor team have really pushed forward in this kind of field of analytics of cosmogenic nuclides, which is really, just has been an engine of innovation. So there's a lot of direct connection, and then we have also, of course, the cosmogenic connection between our work. So what I'm talking about today will be just ice sheets and glaciers in the warming world. What happens to them? Yes, they melt, but what more can we say about that? Then what does it mean for sea level rise, and also particularly its fingerprints? And eventually what we really want to do is the evaluate the impact on coastal communities and see if we can make the situation better there. So, and then the Greenland ice sheet is very much in a worry of us, and I will show you why. And then finally, the mountain glacier. We have a mountain glacier program that has the goal also to evaluate the impact and the influence of the melting mountain glaciers on the sea level more and better, but also to kind of come to a first order, more direct even problem, which melting mountain glaciers create a huge water crisis in high mountain areas. And finally, I want to just basically end with CEREGE, what is next? What can we do? What has to change? Where are we in climate science and climate? Where are we as scientists in the climate crisis? So I don't have to show you that. Our planet is heating, you know that, and the Arctic is heating particularly. That's a red blob on the north. It's kind of 3 to 4 times heating, or faster heating than the rest of the average planet. And in the middle of that, we have Greenland, which the Greenland ice sheet we are, like I said, very worried about. If it melts completely, it's more than 7 meters of sea level contribution. And to the right, I think several colleagues have shown that already. It's kind of the prediction of sea level contribution from the Greenland ice sheet and Arctic ice sheet and the glacial mass loss. So I want to say 2 things here. I can almost guarantee that the Greenland curve, even the red Greenland curve, which is the most aggressive one, is way too optimistic. Greenland will contribute way more. And then I also want to point out, and I come back to that the mountain glaciers actually have contributed more so far to the sea level than either of the ice sheets, and will continue to do so probably until 2100. So they are really reported in that aspect. And then coming to communication of our science, that one of the big problems is that we have these relatively small numbers that just represent catastrophes or really disasters. And one of the aspects, the classic one, is 1 degree warming. It kind of sounds like everybody just shrugs the shoulders if you say there's a 1% warming. So how do you translate that? How do we bring the magnitude of a 1% warming across, really, to not colleagues, but to decision makers and to the broader public? The same is true for sea level rise. It's kind of, in the moment at millimeter per year, and that's already a problem and impacts us. So 10 centimeters of sea level rise is actually a lot, and it's a real problem. 0.5 meter is a disaster for coastal communities, and everything above is kind of getting into the epic disaster space. So there is small numbers that represent enormous impacts. And that's where the climate communication comes in, which is really, I don't have a solution, but we have to kind of tackle that, and we have to really rethink that completely, I think, how we move forward with that. So I just want to show you that it's Greenland now, and if it contributes 1.5 meters, which is a ton, and would it be a disaster, you still have an ice sheet. So it's kind of smaller at the margin, but it does not look like it's completely falling apart. So, so that's how it looks when we are in real trouble already. And the second point that I want to make, which is also often forgotten, is it really matters where ice melts. And I love this paper from Eric Laroure. That's a few years old now. What you see here is can I use that thing? Oh, no. Do you see my cursor? Oh, yeah. So what you see here are these maps of Greenland, obviously, with different cities, and that is kind of representing of the impact of how much does the sea level go up in these different cities across the US if certain areas of Greenland melt. And it's kind of the quantification is 1 square kilometer is melting in, and how much does the sea level go up in Los Angeles or New York or whatever. And you see how locally specific that is. So you see a huge difference between New York and Los Angeles. So Los Angeles would be way more impacted if Greenland melts very quicker, and particularly if the east part of Greenland starts melting, while New York is much more resistant and would feel the northern part. And and Miami is very sensitive to the melt of northeastern Greenland ice sheet. So what I want to say here is without knowledge where the ice melts, you are not able to make a proper prediction of sea level rise in these cities. And we don't have that in any prediction so far. So we have to really look into that. And that's just a conceptual model, but the effect is clear that we have not only to know if Antarctica versus Greenland versus mountain glaciers melt, we have to know where the ice sheets melt. We can do that, I think, but it's just really a new challenge. Cosmogenic dating, I really don't explain that here. I mean, you are so leading in this, and you have probably seen so many cosmogenic talks. There is cosmic rays coming down to Earth's surface all the time. So for this talk, it's really, surface gets bombarded with cosmic rays and cosmogenic nuclei are produced if there is no ice on top. If there is ice on top, then the production stops. And an entire family of these cosmogenic nuclides is produced. A few are stable, but most of them are radioactive and have different half-lives. So what is also kind of, you can think about, if there's no ice, then you have exposure and the production happens and you have an accumulation clock. So the more cosmogenic nuclides, the longer the ice-free period occurred. If the ice comes back and the production stops, the nuclides start decaying. So you have a decay clock. And if you measure several of them, you can really quantify how long the ice sheet is on top. That is really all that matters in the moment. We have a growing number of nuclides that we can use with a growing spectrum of half-lives, which is very important. That gives us better and better handle. And the other thing that is important, somebody said that already here before, one of my colleagues, the production goes down with depth. So this is the top of the rock here, where you have full production. And then, that's a logarithmic axis that I don't like that much. That's a linear axis. So you see that's a meter down, 2 meters down. You see that production goes very fast down. And after about 4 meters, you have basically a horizontal production line, because that's where muons produce. Doesn't matter what muons are in the moment. Up here, it's totally neutron produced. They are kind of very effective, but also get attenuated very fast. So you have this exponential curve here. And that will be important, because if you do a depth profile and you can measure this part of these curves here, then you can actually reconstruct the entire profile in the past, and you know how much material was eroded. I come to that in a second. So that's the summary slides of what I just said. I scanned quickly through that. So exposure means no ice. You have production. You have accumulation of accumulation clock. Ice comes, stops the production right away. Then the decay starts. In this case, we have frequently we use aluminum-beryllium ratio, also because we can measure that so well. And you know the production ratio very well. So it's about 7 times more aluminum produced at the surface than in quartz than beryllium. And the decay half-life is about 1.5 million years. So if you come after time t, drill through the ice, sample the bedrock, then you will kind of be able, and you measure below production, then you can time the existence of the ice sheet on top. That's the aluminum-beryllium decay. Half-life about 1.5 million years. That's the useful timescales. And you already see if you add different nuclides and more nuclides, you will get a broader and broader application spectrum to this. The last thing, which I also said, is kind of the importance of depth profiles. So if you drill through ice or also in front, and you have lost recently part of the rock to erosion, which happens, of course, under ice sheets, and you kind of measure the rest of that, like here, and you see the curvature. So you are in the upper area of the production profile, then you can extrapolate to the top, and you know where you actually were. So that is also something that has been done a lot, and kind of is really that's really important to do. So we measure the concentration of nuclides, gives us the exposure. Ice-free time, ratio of nuclides to burial age, time the ice sheet is on top, and depth profiles give us correction for erosion. So we have used that now in total of four cores and sediment deposits underneath the Greenland ice sheet, and that started with the GISP2 core, which is now that Bob Finkel and me kind of published, the latter publication 100 years ago. What we do is we do these camps on the ice, and that's that's a smaller camp that only went through 500 meters of ice. But it gives you a feeling for the size of the enterprise. It's substantial, but it's not undoable. And the NSF has now developed these kind of drills that can go through hundreds of meters of ice in one field season and then sample the bedrock. So that's called the ASIC drill, and that was one of the recent very successful areas. And also, by the way, this is Prudhoe Dome that comes back, so just that huge dome. If you look at the map, it's actually only a tiny spot compared to the Greenland ice sheet, but it's a huge and massive ice dome. And you can never imagine that it ever has melted when you are on top of that. So what we are doing is really interviewing the rocks underneath the ice. So we take basically a drill through the ice strategically, and now strategically. At the beginning it was just completely into the blind, and ask these bedrocks, when have you been the last time ice-free? And then how long was the ice on top of you after that? So that's really a first-order interview technique, and that's how you can see that. These cosmogenic nuclides are nothing else than interview tools for rocks, asking this the answer, trying to get constraint of exactly these answers. So, and we go through these ice sheets very quickly with this ASIC drill and the Rinky drill. So that's the GISP2 bedrock core that we got, that Bob and me got in, 2014, after a long fight with the sample assignment committee. They finally gave that to us, and that's published, and some of you might have seen that. We did not expect to measure any cosmogenic nuclides because it's under 3 kilometers of ice in the middle of Greenland. But we measured quite a bit of beryllium, and also on the left, the red sample size, the beryllium. You also kind of right away see it's not a straight line. You see a production profile in beryllium-10. By the way, in that moment, we know we are totally in business and can do stuff that is really important. The blue is the aluminum. So we have in two samples the opportunity to look for the aluminum to beryllium ratio. And so the first order result was the aluminum beryllium ratio in both of these samples was not 7, it was 4. And that takes about 1.1 million years of ice cover after prior exposure, that this ratio goes down from 7 to 4. It cannot be longer on top, because otherwise the ratio would be even lower. So what this ratio immediately tells you is a maximum time the ice sheet can be on top. It can be more dynamic, it can be gone. You can get these isotopic compositions with more exposure, but it cannot be more stable. So it gives you a most stable scenario, and that was 1 point. So by that moment, we knew that Greenland was ice-free relatively recently in the geological past, and suggested here, that's the canonical climate record, the benthic 018 record here with the 100 kiloyear world, last 800,000 years, and the Pleistocene transition, and then the 41 kiloyear world. And these are the 3 scenarios that we suggested as examples that were possible with our isotope data. So the most stable one here is 1.1 million years of ice cover. Before that, it was a substantial period of exposure. The beryllium told us that we need actually more than 100,000 years of exposure total to get this signal. So you have to somehow piece together a long time of ice-free as well. I was favoring back then, clearly, that scenario, simply because I was thinking, well, probably Greenland melts when it's warm. So these are the super interglacials, the warmest period. And I was expecting that we see some kind of a ice-free Greenland there. And then at one point, Joanna Charton came to Lamont, and Bob and me have measured with K5 field the chlorine-36 data back then, but it was really, really complicated. I don't go into that, why this is complicated. It's very, very low chlorine-36 concentrations, and it took Joanna a month to really come to the point where we absolutely are convinced now totally that there is clearly cosmogenic chlorine-36 in that GISP2 core. And So she has really sunk her teeth in that project, and has worked with Ali Balter-Kennedy, also with the depth plotting and the fitting of that curve, and is now pretty close to submit a paper. And that's just the raw data of the chlorine-36 as we have it now. We have 4 samples. Those 3 down here make sense. All of them are consistent with the beryllium aluminum, so they are not kind of completely off. But we cannot explain that lower concentration on the top sample here in the moment. So we are focusing on these 3 that seem to have a depth profile shape as well. And what the basic result is, I mean, there's a lot to say. It's a complicated process. But the take-home message really is that, so what Joanna did here is kind of, she took all the data, all the 3 nuclide data and the possible erosion scenarios and modeled those. So you kind of basically created 10,000 Monte Carlo runs with all of the runs kind of figuring out constellation of exposure baryl that were feasible and fit with the aluminum, the beryllium, the chlorine, and the erosion data. And that's what you are getting. So it's again the same timeline, and red means probability of ice-free Greenland, or the ice-free is 2, so Greenland melted. And you see very quickly that the biggest, so there is a clear change from, oops, where are you? Here. There's a clear change from a lot of red in the 41 kiloyear world, less red during the mid-Pleistocene transition, very little red in the 100 kiloyear world. So what this indicates is just the data as we have it. They don't exclude an exposure, so Greenland ice-free in the very early 100 kiloyear world, but it's much more likely that the last time Greenland was really ice-free happened in the MPT or the end of the 41 kiloyear world. So the Greenland ice sheet somehow, I was wrong. So my kind of favorite scenario was it's most likely not, or it's not, we cannot do that anymore. So it points to this maximum stability scenario that there was ice-free before in the 100 kiloyear world, and then frequently and long. And what this means is the Greenland ice sheet somehow changed configuration completely between the 41 kiloyear world and the 100 kiloyear world. The 100 kiloyear world is the period with very cold ice ages as well, and has a 100 kiloyear cycle, so an ice sheet has really time to get to the full configuration. And the 41 kiloyear world is much higher frequency, and the ice ages and the amplitudes in general are not as high. So maybe the entire configuration of the Greenland ice sheet in the 41 kiloyear world was just much closer to these famous tipping points because it was always smaller. And in the 100 kiloyear world, it just got to a size that it melts, but it never melts completely because it's just so robust and stable. So that is a take-home of Joanna's work. And again, she did a brilliant job. This is not an easy, chlorine is not an easy nuclide. But she also, with Ali Balter-Kennedy, developed an enormous amount of toolkit to deal with chlorine-36. So that is a real progress here. So very quickly, we kind of now have the chance to go strategically to the Greenland ice sheet or to any ice sheet and drill. And the Green Drill project is the first one. We did that where we targeted the northern margin of the Greenland ice sheet. I'm leading that with Jason Briner, who's a wonderful colleague from University of Buffalo, without whom I would never have worked in the Arctic in the first place. He's a mostly field geologist and a brilliant climate scientist as well. So we have 2 data points here. We went to Prudhoe Dome, and we went last year to Joining Louis Land in the northeast. And I show you where we are with the Prudhoe Dome core. So we kind of drilled through 500 meters of ice into bedrock in the middle of that, and through 100 meters on the margin. And we have a ton of, the transect basically of the bedrock here in front of Prudhoe Dome. And that was the first field season in front of the ice, and that gives you a nice, that's how the ice sheet looks like, how the base looks like under the ice sheet. So this is very low erosion, very cold-based area here, but it still gives you a feeling for this. You can drill into bedrock, you can drill into sand, you can drill into sediment, you can drill into a boulder. And I mean, we did all the radar on Earth to figure out where we are drilling, but it's never good enough that you can really see the grain size of what you drill. So there's a substantial risk of just failing because you don't know what you are drilling into. But it turned out, brilliantly. We just were lucky. And also think that one of the take-home messages that the bedrock underneath the ice and in front of the ice is just an almost perfect archive for these cosmogenic nuclide techniques. So that's the core that we are working with. It's kind of, we drilled into several meters of frozen sediment, and then after about 3 meters of that, we kind of went into this classic Precambrian Arctic shield rock, this kind of gneiss, wonderful, and all of that has a lot of useful minerals. So we have sediment on top of bedrock. And so now I'm coming to that a little bit. And all of that, by the way, if I will kind of feature her in a second, that is kind of Ellie Balter-Kennedy was the one who finished the field season. Without her, we wouldn't have the sample in the first place. And she's now working and has done an enormous progress with the theoretical aspects of fitting these data profiles. So the bedrock core, so here there's one whitish Arctic shield rock. The beryllium profile is here, and again, you see already that it's curving. And as I told you, in the moment we have that, we can extrapolate, and will get control over this in terms of total time of exposure. And the aluminum-beryllium ratio is measured, but it's very low. And then on top, we start going into this here. It indicates it's still kind of a skeleton rock, so it's not completely only sediment, but kind of a core skeleton of weathered rock, but a lot of sediment washed around it. So Ellie took two kinds of samples. She first sampled the skeleton and did a depth profile with that, and that is that data. So it's a perfect continuation of the bedrock here, and kind of we can use that even better to make the fit better, to extrapolate to the surface. And then she measured the sediments around it, and you see they're completely, there's a logarithmic axis, so they're completely off here. They're way, way higher in beryllium-10 and don't fit that profile at all. And then we go into a mix of cobbles and sediment here, and the chaos continues, if you so want, from the sediment. There might be a cobble or two that fits into this profile, but we are not using those. We are just using those for the fit here. So what this means already is just indication about how complicated sediments are. If you have frozen sediments under ice, it's also a wonderful archive, and it might be even, some would say it's more interesting because you have paleoecology and paleobiology. It's an archive of paleobiology. But you have to figure out basically grain by grain, where did this grain come from? How did it travel here? When it was last time exposed? Was it buried somewhere else, etc.? So it's a very complicated archive, but it has huge potential. So once again, hail to Ellie. She starts on Tuesday her faculty position at Tufts, and will start her own group and her own lab. And she just really kind of, in her PhD that she did in Lamont with me, she kind of developed the entire theoretical framework of this, and this is ready, and she will kind of publish that. She's actually planning to do an app, so we can use these downcore data and kind of just really, for people like me, who are kind of complete idiots when it comes to modeling, just type in this data and then get the exposure time, the burial time, and the erosion rate, that is, or the total amount of erosion. So this is, I'll just show you a few nice pictures here. That is that's the sediment part of the top core. And we also did CT scans, so that's a visual reflection, and if the animation works, then it will switch, yes. So that's now the X-ray, high-resolution X-ray, and the colors give you density. So the yellow color is high density, and the blue is water. So you kind of see the range from I don't know, 3 grams per cc minerals and to 1, which is water. And this goes through the entire rock, so you can really, really do a lot of sedimentology, which we are also doing. So in this core, in the Prudhoe Dome core, there was about 1 meter of rock is eroded. So we kind of could, by extrapolation, could figure that out. The aluminum beryllium ratio gives the apparent total burial age of a lot, of 2 million years. And it gives also a total, the beryllium numbers give you a total exposure time of 1.5 million years. So now you have to piece that somehow together. What this means is there's information over the million-year scale in this core, and the more nuclides you have, the better you will constrain the possible scenarios of what happened at Prudhoe Dome. So, I mean, that's what Ellie is doing. She's kind of taking the climate curve and makes a random, or kind of decides on a threshold, and then kind of tells the model, here's at 3.5, benthic cutoff is 3.5 per mil, and everything above is cold, and there's ice on top, and everything below is warm, and the ice is gone, and that is kind of one of the possible scenarios that would explain, that would go with this data that we have from the Prudhoe Dome so far. I mean, there is much more coming. There's one update we also did. I don't know if you have seen that on the core sketch. We have the top piece. We kind of sample in the dark and send it to Nathan Brown, Caleb Walcott George, PhD student, Green Double PhD student, University of Buffalo with Jason Briner. He leads this study and did OSL dating on that. And that came back with a very solid number of about 7,000 plus minus, I don't know, 1,000 years. That means, and that the burial age, the OSL age of that sediment gives you the last time this sediment has seen the sun. So it's almost certainly kind of a direct dating of the last ice-free period, and that's kind of, we just got reviews back. This is more or less accepted at Nature Geoscience. So there was Holocene exposure in Prudhoe Dome. So that's from the young side. We kind of get information from the young side. We know it was gone, the Holocene. We know the total number of exposure, and we know the total number of burial, and we know the erosion. So that's a start, and now we have to fill in with all these other nuclides. Once again, looking at this plot, keep in mind, take home, if you see, and you will see much more studies coming from frozen sediments under ice, it's incredibly cool because you find, again, ecology, but it's also incredibly complicated. And the forensics of cosmogenics to ask all these grains individually, where do you come from? We will see how far we get, but that's what you have to do. You really need to know where this sediment comes from. And in a way, you need to do it grain by grain, which is impossible, of course, but you need to, so we'll see. That's the frozen sediment is incredible archive, very complicated in the genesis. So these are the 4 cores that we have so far, data I showed you from GISP2. Camp Century, I don't show you, I will show you the papers here. There's also a very similar burial scenario, or the burial, cosmogenic burial and exposure in concentration in the Camp Century sediments, then it GISP2. And there's an OSL date that recently was published by the University of Vermont group, which is leading that part, that gives an indication that there probably was Camp Century was ice-free about 400,000 years, so it's during stage 11. So from these kind of 3 or 4 point measurements, we kind of really have a framework together that was just not there before. And in a way, this is, so Greenland was ice-free and contributed more than 7 meters of sea level, at least once in the recent geological past, probably at the end of the 41 kiloyear world. It was much more dynamic and unstable before the 100 kiloyear world. Camp Century, so 1.5 meters of sea level rise, was probably ice-free 400 kiloyears. And Prudhoe Dome, which is about 30 centimeters of sea level contribution, was gone in the Holocene. So that's what we know from these few point measurements. And again, it's kind of basically the only direct information that you can get from these ice sheets. And there is no reason not to continue that. So we are really kind of, I think we are there. And we also worry because Greenland melts again, and we will pass the Holocene warming, Holocene warming period forcing in years, or at best in decades. And the question is really, when do we approach a 41 kiloyear type Greenland ice sheet configuration again, in which case we know it's really, really unstable. So these are things we have to worry a lot. You can also do the same game, just by the way, in Antarctica. We can have the tools now to do that. In volcanic rocks, the same thing with pyroxene. So that is also kind of ready to go. And don't forget the mountain glaciers. I mean, you can also really do a lot of these studies with mountain glaciers. So in general, the basal zone is kind of, in a way, a new, completely new archive for this. Or it basically seems to be an archive that has almost waited for these cosmogenic methods because it talks to us. We have asked it blindly 4 times and it just keeps talking and gives us this information. So that's an archive. So far we have not a single failure. So we need to continue doing that. There's a lot of work to do. We can start now the sea level fingerprinting map with the ice-free Prudhoe Dome and also with the ice-free Camp Century and see how that impacts the different shorelines. The one gap we have, which is massive, is that the impact on communities directly and the inclusion of the community response and the resilience and what it actually means to the community, which is really the goal, we haven't even started with that. So this is very crucial to do. And then it's a really strong motivation to think of a program to continue that drilling around Greenland. You can do that all the way around Greenland, and in principle. And again, it's a big program, and it will take 10 years plus, but it's absolutely doable. So the last thing I want to show you here, very quickly, where are we in time? Timing? Oh, okay, good. So what I want to show you that's really very fresh off the press is we took one of these Greenland cores, not the Prudhoe Dome one, was another one for reasons I tell you later, or I can tell you outside, and measured with sent these samples to incredible Lou, who is an atom trap trace analysis genius, really, and changes the field completely in the moment by creating these measurements that we always wanted, and once of a sudden with this technique, with this laser technique, he can count individual atoms and can do it now fast. So they have done, he's in Hefei in China. So that's what you see here is the first calcium-41 depth profile, I think, ever in rocks. So that's the top of the rock here. And then you see the production going, the concentration going up, and then it goes down. And that's exactly in accordance with the theory, because calcium-41 is produced by very slow neutrons from calcium-40, like neutron capture. And what's happening is kind of two things. So here in the top level, the neutrons come down here fast, and they slow down, and they get a kind of a maximum of the thermal neutron is about here, and that's where the maximum production is. And you lose produced calcium-41 by diffusion, you lose neutrons to the surface in this direction. So the top surface has a little bit less neutrons than lower here. So there are theoretical models that show exactly this bump. We were expecting to see that bump in the chlorine-36 world as well. We never really saw it in that clarity. So that is a lot. It's just the first measurement. There's a ton to do. We have to calibrate this entire method, but it's basically, I think it's that plot alone shows that we have to do it, but we will get this done, and then the calcium-41 is available for us in the rock field. By the way, also for archaeology, might be a real breakthrough that you can measure now the absurdly low amounts of calcium-41 in terrestrial materials. So the production profile tells us this is cosmogenic, so this is really from the cosmic ray, neutrons, cosmic ray neutrons coming. And the other measurements, they can go now down to less than 10 to the 5 atoms per gram calcium-41. The ratios are here, which is above blank. It's about 3 times 10 to the minus 16. So the reason why this calcium-41 is so essential is it has a 100,000 years half-life. So if you compare that, combine that with beryllium, for example, and you have a scenario of ice-free, some rock was ice-free during stage 5e, 100,000 years ago, 120,000 years ago, and then the ice sheet came back and covered it, calcium-41 will be the tool to tell you that. So that is really essential. And so again, over this climate curve, you have now basically, or we have now kind of tools for almost any of these interglacials. So if you want to check if something was ice-free during stage 9-11, you probably choose chlorine-36 to beryllium. If you want to check stage 5, then you use definitely calcium-41 to beryllium. For the longer time scale, you do 2610. And for the very young Holocene, which we are also doing in the moment, you do C14 beryllium. So all of that is, the calcium needs work, but all of that is doable. And you can even go more exotic and do beryllium neon or beryllium manganese 53 even, but that's a little bit further away. So very quickly, the last 3 minutes, I want to show you something completely different. And that's because it's so low-hanging fruit, or so kind of surprising. So the mountain glacier contribution to sea level is really not well established. And there's basically no reason, and this program that we got funded from the NSF has the goal to improve that. It also has a big educational component. We do in Patagonia kind of glacier field academies, which are wonderful. All of these kids are modelers. Many of them have never seen a glacier before. It was very transformational. I'm doing that with Summer Rupert, who is kind of the mountain glacier glaciologist, and she's incredible. And Jackie Osterman, who is a sea level fingerprinting expert. So again, they are relevant. They only have about half a meter to give, but they give it fast, and we have to understand that. There are predictions what happens, how mountain glaciers look at the end of the 21st century. So there's a very nice paper of David Rounds that came recently out in Science, and that's shown here. But they do it global. They let all the glaciers run until 2100 and melt, and then make this map here, which is a very, very good start. There's one problem with that, is that a glacier is integrating, so that's based on satellite data. So it's about 25 or 30 years of satellite data extrapolated to 2100. The problem is that glaciers integrate temperature and climate signals over hundreds of years. So to calibrate a system like that with 25 years is just not very solid. You need a longer perspective, and that's where the cosmogenics come in. So we want to help with that. And in the process, I didn't have that on the map really. In the process, we recognized that we work a lot in Santiago with our colleague Esteban Sagredo there. And there you run into this water crisis. Santiago is 8 million people, and it's growing. And it has exactly one glacier catchment that is responsible for the water, for all the water of Santiago. And these glaciers are melting like hell. And there is really very little knowledge and understanding of what this means in the 10-year time scale. So we are trying to raise awareness and kind of work with our Chilean colleagues, because Santiago already has a water crisis and will be a real disaster. So what we are contributing is that. We are contributing, hopefully, a longer-term glacier response curve over 100 plus, 150, 200 years that is much better usable for calibrating that, and then evaluate the sea level change. And Jackie Osterman and her group, there's enough melt since the little ice age in Patagonia that you can really actually make a sea level fingerprinting map. So you can do the same thing that Eric Leroux did, and can just make that for glacier change in Patagonia. And then the water crisis in the high, Santiago is just an example. It's kind of so many other cities in the Andes, but also in high mountain Asia have exactly the same problem. And we need better predictions, but we also really need a very, very transdisciplinary approach to tackle that. And it feels to me in the moment that there is a lot of direct stuff we could really contribute. So I jump over that. So, yeah, right, so that is kind of a question that is basically the direct interface of climate and glacial science and climate justice. In a way, the climate crisis is getting so out of hand and so extreme that we really kind of directly, our basic science is directly meeting with what the society needs. And just an example is here, that's the water consumption map of Santiago. So the water that comes here and it comes less and less. And these are the rich communities. They are using all the water. There are the golf courses and everything, and then it gets less and less down here. And then this is the election results of the last election, and Boric is a social democrat who, among other things, wanted to take the privatization of water rights back and make a water equity and program so that all Chileans have access to water. And red is CAST, which is kind of a Trump-type, hardcore, right-wing, billionaire-serving president. Boric won this election, but kind of and that's a map that's produced by CR2, which is an incredible center in the University of Chile in Santiago. So the match of these two maps is kind of just, this is our glacial science here, and that's the election result. So much to interface between science and society. And we also have a book coming out that is kind of making the case that the only thing forward is cross-disciplinary. We need to kind of completely rethink everything, I think. That does not mean climate science has no place, but we have to team up in a much broader team and more interdisciplinary team. This is Rebecca Marwege, the lead editor. She was actually a student helper originally, but she's fantastic and has done most of the work. She's now started in Paris at American University as a professor here, and Nikaka Igdwat in Columbia, who is a political science colleague. All right, so I leave you with that, I guess. So it is really kind of time where everything comes as a storm on us. So the environmental and climate science is very fundamental, and it gets closer and closer in the focus of just for survival of humanity on Earth. So we really need to team up with many other disciplines. We need to take care on science in general. There's really not much difference anymore between taking care of science and taking care of democracy and liberty. We have to think really much more to talk to policymakers. We have to really get out of our ivory towers, simply because the danger is right on top of us right now. All right, so with that, I want to end that saying that CEREGE really in many aspects is right in the middle and really well equipped to become a lighthouse in all of that. This kind of new decade or plus and the new role of climate science in society. There's really so much here in terms of the structure, there's climate, CEREGE, excellent climate science, environmental science, OSU, PTEAS, the Climate Council. By the way, AMU is the second university on Earth that has put climate into the undergraduate core curriculum after Berkeley. This is a completely underreported fact that needs to be top on the webpage. This is actually really incredible. And so well done here, as in so many others. It's just an example of how advanced and how much potential there is here. And then once again, CEREGE and AMU have been a beacon of academic freedom, and let's do everything to keep it that way. Thank you.
Thank you.
I'm sorry that I went over.
Thank you very much, Joerg. Maybe we have time for a few quick questions.
Thank you very much, Joerg. Very inspiring talk. So I have many questions on the cosmogenic data set, but we'll leave this for. Now, more a personal question, actually, if I may. As a scientist that works on, acquiring data, on, retreat of glacial and then Greenland. But we see now that there is like a tipping point in your career where you went into climate justice and climate action with the last program that you showed us, Magic. So was there a tipping point where you decided that you had to go into that aspect?
Yeah.
In your, and so if there was one, what could you tell us what triggered this, or what led to the conscious that you had to go into action as a scientist?
Yeah, I mean, so one is the one that we probably all have. So I just realized that we understand more and more about the Earth system and the climate system, and we are really getting smarter and smarter, and the impact on real politics and on real life has been almost zero, or by now negative. That's frustrating. The motivating aspect was that in the classroom, teaching climate, at least at Columbia, it just became more and more. 10 years ago, this was a classic climate science, basic science class, and the students kind of just demanded more and more another approach. They are fine with climate science, and they're also fine with physics and chemistry if they need it, but they ask always, why do we need that and for what? So there was a lot of, but at one point it just struck me that that approach of science is probably the much more appropriate right now, that you're not just thinking of, all right, I want to understand that because I like to think about it. It's just, it really has a goal. And in the classroom, this was very impressive. And I mean, there's this kind of what I call, or what I feel like is an academic reversal. I have more and more in this discussion, why are we actually doing this? The flow of knowledge goes from the students to me. I kind of feel kind of strange because they should be paid and not me, because they know so much more about the entire justice. And so that was kind of a really positive thing, that they basically said, that's what we want. And that's kind of in these Ivy League type universities, it's really that students have really a lot of saying in these, and that was very positive. So yeah, these two things kind of got me. And then I must also say that before recently, the federal funding agency, I'm an NSF guy, so I mostly have written NSF proposals and got funding by the NSF. And the NSF was opening up more and more to integrate social scientists and artists. And these two, both the Green Drill and the Magic program, they have social scientists involved, and they have film art people involved, and that's all funded by the NSF, so it went in the right direction, and I recognized how incredible that is in terms of broadening your perspective and how much better they are in telling the story, for example. So that's one of the things that I feel really very incompetent looking back, how in the communication that I should have had that insight much earlier in my career. And in a way, it's also every NSF project that is climate should have a communication person. And so, yeah, so that were the three moments.
Thank you very much.